Hello, my name is Lauren Adoram-Kershner, and I'm going to be talking about some work that colleagues and I at the USGS Astrogeology Science Center completed to create a automated DEM generation pipeline and subsequent serving procedure for Kaguya TC and MRO CTX data. Please take a moment to notice these disclaimers that any use of trade, firm, or product names is for descriptive purposes only and does not imply endorsement by the U.S. government. Additionally, this information is preliminary and subject to revision. It is being provided to meet need for timely best science. The information is provided on the condition that neither the U.S. Geological Survey nor the U.S. government shall be held liable for any damages resulting in the authorized or unauthorized use of the information. Alrighty. So our motivation for this project is that digital elevation models, or DEMs, are foundational products within a planetary spatial data infrastructure. They can be used to support scientific applications such as geomorphologic analysis or engineering applications such as candidate landing sites. This is not an exhaustive list. There is many more applications of DEMs out there. To get an exhaustive list is impossible. Our other motivations include the volume of stereographic images coupled with the manual generation standard for DEMs means that there is a lot of DEM potential. To illustrate this point, what I have on screen is the footprints of DEMs, potential DEMs from the Kaguya TC dataset. Now, you can see that the distribution is global. This may not all of the DEMs may not result in viable DEMs. Some of the images may be of insufficient quality, but the potential is impressive. And due to the need to prioritize cartographer time for the manual generation of these DEMs, when DEM generation is funded, it's usually targeted on more popular areas or areas of interest, and it does not cover the full data sets. And this subsequently results or has resulted in DEMs for a certain data set being served across various research institutions, all with their own flavor of processing. And this in itself isn't bad. What becomes an issue is that it is difficult to trace the different flavors of processing or the provenance of the DEMs, how they were actually created, because that information is typically contained in separate papers, abstracts, I don't know, conference presentations, and not served with the DEMs. And so what we did is we created an automated pipeline using USGS ISIS software and the NASA Ames stereo pipeline software, and we applied it to MRO, CTX, and Kaguya TC data. We based our actual DEM generation pipeline off of previous work that Mayer et al. Did to automate CTX DEM generation, and the process is outlined below. It's a little complicated. I'm going to break it down real fast, but my eyes did cross when I first saw this, and so what we ended up doing is simplifying it so that we could make sure that our DEM generation and subsequent serving procedures worked well before we got a little more sophisticated with our DEM generation pipeline. And so what Mayer et al. Did is they ingest from raw data in case new data becomes available from the missions team or new ISIS functions for that data set becomes available. And then they do an ASP bundle adjustment to vertically relatively align the stereo pairs to one another. They then run parallel stereo and point to DEM to create a low-res DEM, map project the cubes, and feed that into the same parallel stereo point to DEM to create a full resolution DEM, align the full res DEM to ground, apply the same transformation matrix to the low res DEM, combine the two, and then you receive your final product. And like I said, we simplified this so that we could get the entirety of the DEM generation and serving proof of concept completed. And so we simplified it, integrated it with metadata generation and a serving procedure. So our more simplified processing is on the screen for MRO, CTX, and Kaguya TC, largely conceptually the same with CTX having one more step. So we, again, do the ingest from raw data, an ASP bundle adjustment. We do a parallel stereo, which is the bulk of the DEM generation in ASP, feeding in these stereo config files, the CTX config.stereo and the CAG-TC config stereo, in order to parameterize that parallel stereo step. Point to DEM to get our initial DEM. We align to ground, and then for CTX, we have this additional step, DEM geoid. It doesn't alter our DEM in any way. It just ensures the elevations are measured off of the mola aeroid as opposed to what point to DEM defaults to, which I believe is just a triaxial ellipsoid. The real novelty of our work, though, is how we're serving the data. So typically what happens is the DEMs are served. And so we are doing that. DEMs are served as cloud optimized geotiffs. But then we create some associated products such as DEM hillshade and the ortho image that comes out of the DEM processing. And then we create associated files to really allow for transparency in how we created our DEMs. We create a provenance file that holds every single ISIS or ASP command that we ran to generate our DEM. We also give the ASP configuration, that stereo file that I pointed out that feeds into parallel stereo. We provide that alongside the DEMs. We also generate two different quality metrics. The first being, they're both displayed in figure 3 in the bottom right-hand corner. And the first being summary statistics describing our final alignment to the ground altimetry data. And then on the right, we give the ASP intersection error raster, which is essentially a measurement of how well did the bundle adjustment relatively align our two stereo image cameras. And the scale on that is that the darker values are 0 and the lighter values are 6.8. And so you can see at the top of that raster for this particular example, where we have those no data pixels, the grayed out pixels, you see that the intersection error raises a little bit, and that intuitively makes sense. But the purpose of these quality metric files is to allow users, since we're hoping to automatically generate DEMs for an entire data set, we're trying to provide as much information for the users to make judgment calls as to whether their quality is sufficient enough for their application, because we're not going to get eyes on all of these if we're making DEMs for an entire data set. And finally, to raise visibility, we generate two kinds of metadata, stack and FGDC. Stack is actually how it's searched on our where we serve the DEMs, and the FGDC is served as an associated product. And so including our serving methods, this is what our flowchart looks like. We have, after the PC align step, we take that final point cloud, geodiff it with the altimetry data to see those summary statistics. We then get when we get our final DEM, we create those associated hillshade ortho images. We package all of our run functions into a provenant.txt file. And then, like I said, we take that configuration file used for parallel stereo and we serve it as well. And during this work, we did some benchmark comparisons. These are not validations, but they were very helpful. So what you're seeing on screen is our pipeline-generated DEM on the left and a hand-generated DEM on the right, made in socket set by a cartographer. We're able to process the exact same CTX data through our pipeline. And this just gave us, like I said, a sanity check. When we initially pulled these up before we put that DEM geoid step in the CTX pipeline, the elevations were about 1,200 meters off. And so that set up a really big red flag. We asked some questions, we did some reading, figured out we needed to put that extra step in there. And now, as you can see, the elevations are well within one another, and the distribution of the elevation, like the color map, looks very similar between the two. And the holes, the biggest difference you'll notice is that there's holes in ours and there's not holes in the hand-generated socket set DEM. And these holes, first of all, are very intentional. They're high transparency. We're trying to have high transparency for where data was not resolved so that, again, users can make the best judgment as to whether these DEMs are sufficient for their analysis purposes. But the hand-generated DEMs, the cartographers are actually able to go in, and if there's any holes, they're able to go in and kind of manually fill them in. But since, again, we're not getting eyes on all of these, we didn't want to do that. We wanted very high transparency. And we did a similar comparison with the Kaguya TC data, but we compared it to LROC. We just wanted to do a cross-instrument match instead. And so this particular one, we did multiple benchmark comparisons at multiple sites. I'm just showing one here for sake of time. And so this is located at the Apollo 16 landing site. And again, left is pipeline generated. You can see some of those holes, and the right side is the LROC. It looks like the coloration is slightly different, but that's because in the bottom left-hand corner of our Kaguya DEM, we have a large crater that's not present in the LROC one. And if we force stretch, the distribution looks, to double check, the distribution looks, or the color map looks very nice. Our actual validation is comparing our DEMs to the ground source data. So for our CTX, that is the ultimate MOLA shot data, which is a precision experimental data record, which means it has some smithing, some outlier rejection. And in terms of actual DEM, we compared it against the MOLA MEX HRSC blended global DTM. And so what we did is we brought our pipeline DEMs and this global DEM into ArcMap, created a difference DEM, and that's what's on screen. And the histogram is the values of the pixels in the difference DEM. And so it's really good alignment for CTX. It has a mean difference of 0.09 or negative 0.09 and a very normal distribution, which says to me that the differences are noise. For Kaguya TC, it's a slightly different story. We're using LOLA shot data, which is just a reduced data record. It could contain outliers or systematic offsets, maybe. And we compared against the LOLA Kaguya TC DEM merge. And again, the difference DEM is shown on screen, and its histogram is also on screen. And you can see that there's this non-normal distribution, this sort of tilt present. And that's difficult to tell whether it is caused by our processing or by the LOLA data maybe having some sort of systematic offset, or even if the LOLA Kaguya TC DEM merge has some sort of processing done to it. What I can say is that the other sites that we analyzed and the LROC DEMs all showed this tilt. So we at least are consistent with the community standard of those hand-generated LROC DEMs. And LOLA, another bright side, I just love bright sides, is that LOLA is in the process of being smithed, and so we can always revisit this after that work is completed to see if we need to make alterations to our lunar pipeline. So that is all I have for today. Here are my references, and I think at this point we cycle into questions, but thank you so much for attending. Bye.